This video, we're going to prove the following theorem. If the prime factorization of n greater than 1 is p1 raised to the k1 times p2 raised to the k2 all the way up to p sub r to the k sub r, then the positive divisors are n are precisely integers of this form where the a sub i's these exponents, the power of p sub 1 is no bigger than k sub 1. All the way down to the power of p sub r is no bigger than k sub r, and it's positive. Remember, if d was equal to 3 times 5 times 11, but some of the exponents were negative, there's a problem here. This is not an integer because it's divided by 3 to the 4th. And 3 doesn't go into 5, and 3 doesn't go into 11. Nor does 3 go into 55, or 33 does not go into this. So the exponents have to be at least 0. The exponents must be at least the number 0. Okay. Now, precisely. That's a very key word. It basically says if this is n, if this is the prime factors of that n are precisely numbers in this form. That's if and only if. If you have a number, if you have this number, then any divisor looks like this, and if you have a divisor that looks like this, then the bigger number is this. That is, if this is a divisor of n, then n must be in this form. They come in pairs, folks. This is an if and only if proof. And if you like seeing mathematical proofs, then you should subscribe to my channel, as this is all that I do here. I'm going to clean up the board and be right back. Okay, so let's get a couple of simple cases out of the way. If d is 1, that implies that d is equal to p1 to the 0 times p2 to the 0 all the way up to p sub r to the 0. That is a1 equals a2 all the way up to a sub r, which equals 0. That is, d is of the appropriate form. It said that the powers has to be at least 0, and they were. On the other extreme, what if d is equal to n? Well, that would imply that d is p1 to the k sub 1 times p sub 2 to the k sub 2 all the way up to p sub r to the k sub r. And this is perfectly allowed. A sub I can equal k sub I. This implies that a sub I is equal to k sub I for I in between 1 and r. Okay. Now suppose that d is in between 1, d is strictly in between 1 and n. It's more interesting. Okay. Is a factor. D is a factor of n, and and is jammed between 1 and n. Well, that implies there exists a d prime in the integers, positive integers, such that d times d prime is equal to n. Okay, now d and d prime, whether their product equals n or not, they have their own prime factorization. Suppose that d is equal to q1 times q2 all the way up to qs, where qi is a prime. And d prime is equal to t1, t sub 2 up to t sub u, where ti is a prime for I between 1 and n. Okay. So now we have that n. So n is equal to d1 times d2, which is not true. It equals d times d prime. That is, d is equal to q1 q sub 2 up to q sub s. I meant to say n. So far I wrote d, and now I'm going to multiply it by d prime, which is t1, t2 up to t sub u. Okay. Now, I want to write this just a little differently. Let me put it down here. N is P1 to the K1, etc. N is P1 times P2 to the K2 all the way up to PR to the KR, and that equals D times D prime. I just want N written out in front of us. T1, T2 up to T sub U. So that is that. Now, so we have this prime factorization equaling a product of those. Why did I not really call this prime factorization? It really is, but it is possible that D contains a prime that the T's also contain. There's nothing preventing that. Think about why that's true. There's nothing preventing like Q2 equaling TU. There's absolutely nothing presenting that. But they are two prime factorizations, which are two prime factorizations of n. Now, why am I calling this a prime factorization of n? Because it equals n, and all of these are prime numbers. Doesn't matter that I repeat it. 3 times 7 times 5 times 3 times 11 times 5. That is a product of factorization, and I'm making this up. If this product equals 1023, well then this is a prime factorization. We've always maintained prime factorization of a number is unique up to the order. I have every right to put those two 3's together and those two 5's together and maybe put the 7 at the end. So yeah, those are two prime factorizations. Well, this tells us, this implies that Qi must be one of the P sub j's. That Qi, it has to be one of those P's. There's no way around that. So what we get is that D is equal to Q1, Q2 up to Q sub S. This is equal to P1 to the A1 times P2 to the A2 all the way up to PR to the AR, where A sub I is allowed to be 0. Okay, so what did we get? We got that D can be written as that, in that form. Okay, and I guess I should also say where A sub I is in between 0 and K sub I. A sub 2 is in between 0 and K sub 2. Now, if we look back at the very, very top, if I started off with this, I wanted to show D equals that. Got it? That half is done. Okay, so now let us go in the other direction. Here we want to show that D turns out to be a divisor of N. Okay. Let D equal P1 to the A1 times P2 to the A2 up to PR to the A sub R. Of course, where A sub I is in between 0 and K sub I for each I. Okay, so now what does this tell us? We know that N is P1 raised to the K1 times P2 raised to the K2 all the way up to P sub R to the K sub R. And I'm claiming that D, this representative of D, is a factor. P1 to the A1 times P2 is a divisor, which means when you factor this, D is going to be a factor. P sub R to the A sub R. That means I need to find something to multiply it by that equals N. Well, I can multiply by P1 to the A sub K minus A sub 1. That's not true. A1, that's very much not true. K1 minus A1. Why? Because when we add those powers, we get K sub 1, which is what we want to get. All the way down to P sub R to the K sub R minus A sub R. Now, is that enough? Like, I can say that 11 is 7 times, well, if I want 11, I put it there, and then I divide by 7 to kill off that 7. So 11 is 7 times this number. Therefore, 7 is a divisor of 11. No. That's because 11 over 7 is not an integer. I need to make sure that this here is an integer. That is, these powers can't be negative, because if P1 to their, oh yeah, I guess I'll write it. If we had p1 to the negative 2, because this was negative, times p sub 2 to the 3 times p sub 3 to the 4, where p1 was 2 and p2 was 5 and pc was 11. The problem is this is not an integer. It's 5 cubed times 11 to the 4th over 2 squared. And 2 does not have any common factors with 5 and 11. You know, if you had 10 cubed, then yeah, at least one of the 2's can go in, because this is really 5 times 2 each cube. And we can kill off the 2 2's and have 5 cubed left over. But primes don't go into other primes. And no factors of primes go into other primes other than 1, because primes don't have factors other than 1. Okay, so we're gonna come right here. We know that a sub I is less than or equal to k sub I. That is, k sub I is greater than or equal to a sub I. Taking a sub I away from both sides, we get that k sub I minus a sub I is greater than 0. That implies that p1 to the k1 minus a1 up to pr raised to the kr minus ar is a positive integer. Okay. So, what we have then is that d is greater than 0. So d is greater than or equal to 1. At worst, all the remember, every prime is 2 or more. And if all the powers are 0, you're going to get 1. If the powers, if some of the powers, even if just one of the powers is bigger than 0, you know, if the bases are 3, 5, 11, 23, 37, if all the powers are 0, then you'll get 1. But if one power, even if one power is 0, is non-zero, you're gonna get back a positive number. Maybe it would be 3 squared, which means we'll get 9. Maybe 2 of them were not 0. Maybe those 2 were 1, so you're gonna get 15. Maybe this was 2, so I guess you'll get 75. D is going to be at least 1. And d does divide n. Since this is an integer, d must divide this. For the record, this d prime must also divide n. But we just wanted to show that d divided n, and I have a slight typo here. I meant to say that d prime is at least 1. Okay, it's at least 1. That finishes this mathematical proofs. If you're into math proofs, this is the place to come to, as that's all I do is mathematical proofs. See you guys in the next video. Don't forget, watch and learn.